graduate student, assistant director of the Christina Torres Memorial Astronomical Observatory, and a researcher at the Center for Gravitational Wave Astronomy at the University of Texas. Today we will be discussing with us the research involving gravitational waves and optical follow-ups of black hole mergers. Thank you, Mr. Castillo.
Cool, thank you. So I think I need to share my screen really quick, and here we are. All right. So, as was stated just now, I'm Moises Castillo, and let's talk about optical follow-ups to gravitational wave detections. Um, Before I start, though, I do want to go over the who's who, right? I have some images here of on the bottom. So I'm from the University of Texas, Rio Grande Valley. There we house an observatory. The short four-letter designation is CTMO, the Cristina Torres Memorial Observatory, and it was named after Cristina Torres, who was active scientist in part of the LIGO collaboration. She did a lot of work there as well, in doing public outreach. And so it's befitting that this observatory be named after her because we use it as a education tool. Then on the list we have Center for Gravitational Wave Astronomy. We have a group of scientists that is, whose focus is in gravitational waves at UTRGV. We have people that study in all aspects of gravitational waves, including the engineering part, right? So we have people who do optics, dealing with the lasers. The head of the chair of the laser committee for LIGO is one of the professors at our institution. Um, and we have people who work on the algorithms for detecting the gravitational waves themselves. And he's one of the world's experts in swarm optimization, is what it's called. And so that's solely work that's done on computers. And then there's folks like me. I'm an observational astronomer. And so what I do is I look at stars, right? um, and that leads me straight into the last logo. And so it's Toros. And Toros means bull, right, in Spanish, and uh, and it stands for Transient Optical Robotic Observatory of the South. And if you may have heard earlier, I'm actually from the southernmost tip of Texas. And what I like to tell people is when we're talking about Observatory of the South, we're not referring to South Texas. In this case, in the logo, you could actually see one of the southern constellations, the Southern Cross. And so we're talking about the southern hemisphere. And we are working on having a telescope commissioned uh, in Argentina. And so that's one of the cool things. It's a wide field telescope, so we're able to see a large portion of the sky to follow up these kind of events called gravitational waves and look for these things called transients that we'll talk about. Um, Something about when I do like lectures, I don't like to call them as much lectures rather than conversations. So there'll be sections that I'll ask for your participation. If you can use the Zoom chat to go ahead and drop in, what what you think, or if you have questions, you can go ahead and drop them in the Zoom chat. And I recommend the chat just so there's not an overlap of voices that might happen, during these connections. But let's talk about optical astronomy, right? They just out of curiosity. So from this group, I know that you guys do have a optical astronomy section, right? Is this or how much of the percentage of students, or maybe you can say me, I'm part of the optical astronomy group. I'm just curious. I want to get a feel for that. I'll give you a few moments to do that. Now, optical astronomy, and I have my chat window open so I can see too. um, Optical astronomy. So my question is, in three words or less, how would you define optical astronomy? So this is a challenge. I don't want this whole lengthy thing. Just optical astronomy, 3 words or less. What would you say? Go ahead and drop it in the chat now. Hmm. Looking at space, seeing stars, or seeing those stars. Yeah. Looking at stars. Yeah, so there's this common trend, right? Maybe not so specific towards stars, viewing the universe, right? Observation of space. And ooh, light informs science. That's really neat. Analyzing the stars, observing space objects. Space through lenses. Yeah, so that's a very like descriptive way to describe this. And so I actually collected a list of things that I was thinking potential answers that you might say, and they pretty much all fall into these categories. The main one is that it's a visual observation, and this actually is something that is the common trend for all the responses that I got. Some of you might include some observation tool. For in this case, one that I didn't specify was lenses, but in this case, I wrote telescopes. Telescopes could be made from mirrors or from lenses. And one that I didn't see entirely, except for one of them, where light informs science, right, is the sensors that we use ourselves. Here, I specified 2 sensors, but there is a third, and it's probably one of the most traditional ones, and one way that you yourself can do, this thing of optical astronomy. Traditionally, people would just look up at the sky. That's it, right? So since ancient times, people would look up at the sky, write down what they saw, and then from there, maybe there were some stories that would help them remember the positions of everything, maybe help them remember even the brightness of these things. So today it looks a little bit different. And so this is actually an image from us commissioning our new telescope, not in Argentina, but at our own CTMO, which resides in Brownsville, Texas. It's in a local state park, the Resaca de la Palma State Park, and it's pretty cool. It's a gem that's hidden inside of Brownsville. Not even the residents, not all residents of Brownsville know that this state park exists, and it's actually one of the largest state parks south of San Antonio, I've been told. It's 1,200 acres, and it provides this nice, like elbow room and nice buffer from the city lights because it's so large. Um, and we're really excited, to have this telescope. Though this image is probably, I think this was summer of 2019 when we installed this, so it was last summer. Um, the telescope setup itself, though, is identical to the one that is being set up in Argentina, except that theirs is larger than the one that we have. Yeah, so that's it's much nicer. Um, Now, this brings me up to the next point: recording data, right? Recording data, depending on how you've been doing your observations, would look different depending on the times. So I did my thesis as a master's student talking about variable stars. I worked on developing a pipeline for detecting and characterizing variable stars with an emphasis specifically on eclipsing binary stars. And I found this interesting article. There's a group of people that claim that they think inside the Cairo calendar, um, they actually recorded the variability of stars. So we're talking about this ancient Egyptian text, and here they have a square around the name Horus, right? Which is one of I think actually it's like the god of gods in the ancient Egyptians. I might be mistaken, but if I remember correctly, it's like that. And they say here Algol, also known as the demon star, and it's a known variable star. Um, they say that the way that the repetition of the name itself appears in the text seems to coincide with the period of the variability. So uh, this is something. Oh, Horus was the god of war. Okay, so I think that's a little bit more befitting, right, to the demon star. um, and there's other stories where I've seen people also claim they say maybe like this is just a wild kind of far out there, but it was published in the journal for the American Association of Variable Star Observers. They they say like, all right, listen to this. Maybe it could be that embedded within the text of the stories of the ancient Greeks and the constellations is actually stories of the variability of certain stars as well. Just so happens that there's, I think it's Algol itself that represents the eye of one of the Greek creatures, and that it's being tossed. So there's some kind of eclipsing motion that's happening, and they claim like not only did they say that it was a variable star, but also that it was an eclipsing binary star, and um, it's fun to think of it. If it's real or not, that's up to interpretation. Right? Um, then I present this picture. This is a typical image that you would see on something that's called a daguerreotype. The daguerreotype, these are the images that were taken way back when. In the 1800s, they were developing photographic plates. So the way you take images was on a glass plate. The glass plate had a bit of chemicals, usually some mercury vapor, that was then made light sensitive through different like gassing processes. And then they would expose that plate to light and it would capture these images. The thing with this is that you would have to wait a long time before you get, oh, iodine, thank you. And that's right, yes. You would have to wait a long time to be able to just capture the image. And the guy himself, Daguerre, ended up pointing his daguerreotype to the moon. So it's claimed that he was the first to actually do an observation, a visual observation of the moon using the daguerreotype. And there are some images on online if you look up the daguerreotype on Google for the first image. But you'll find that the first image that's recorded is not his. It's actually by another observer by the name of Joseph Wilmer, I think is his last name. And he the thing that happened with Daguerre is that his lab actually caught fire, and in it he lost everything, and so that's very unfortunate. But that brings us up to uh, modern times, right? So on the left you have an image of a typical CCD that's used. This is actually the CCD that we use. CCD is a charged coupled device, and on the right you see the sensor that sits inside of that housing. Um, so you can think of it something similar to what you might be able to find like in your smartphone. You know, if you have a camera, if you do photography, if you look down inside the lens, you know, if you take off the lens, you'll see the sensor itself. Um, Here we have these cooling fans, right? We try to minimize noise, and if you start introducing heat, introduce you know, an excess Brownian motion, you start introducing random stuff, and so we want to keep these things cool and at a constant temperature. Um, right, so that's pretty much it. What I have regarding optical astronomy. Let's talk about gravitational waves. Gravitational waves are an interesting subject. I find interesting. It just so happens I took a class in talking about general relativity, and it was just an introduction. So I learned a little bit, but just enough to be able to explain some things. and that's what I'll do. I'll do with you today. So first, I'll share an illustration of gravitational waves. Okay, so I'm not sure. I know that most of you are already in an advanced level in physics, and so I show you this, but not to scare you. But again, it's an illustrative for illustrative purposes. So here we have Einstein's equations, and this is the bread and butter for people who do GR, who study gravitational waves. Like this is step one. Uh, I open up the book to Introduction to Gravitational Waves, and pretty much in the first chapter, in the first page, uh, they show you this. They say, "Welcome. These are Einstein's equations, and they come from these things called gravitational action." So S is a common letter or symbol that's used to refer to action, and on the left you see SE or S sub E, and that's referred to as the Einstein action. And then the one on the right is the matter action. So the Einstein action contains all the geometry part of space-time, and the matter action contains the matter part, right? So if you have some matter, that's where the action is, or the description of the action is held there. And then we have that delta symbol, and what that means there is we it's the like one of the fundamental things for physics that we do, where we have the variation of the total action and energy conservation, right? So we set that equal to zero, and then from there we get this next part, which are the equations of motion, right? So this is all just to illustrate. Um, I remember one of the things that I when we started learning some of the more complex things in physics, they say, um, trust me. They say, trust me. You don't have to think about it too much. But here on the left side, we see these terms R, right? And R is talking about the geometry of space time. So that's all that is there, right? So we're talking about time and positions. On the right side, though, we have 8 pi big G. Big G is the thing that we're familiar with. It's the classical sense Newtonian big G, and c is the speed of light. So all those are constants. The only thing that's different here is that big T, and T is the energy momentum tensor, right? So, or the stress tensor. And so that is interesting because now on the left side, we have things that talk about pure geometry. And on the right side, we have things that include matter. And so this is the big deal about that we have just geometry on one side and matter on the other side. So what does that mean? Well, we get once, and these are some of the exercises that hopefully maybe if you get interested or you ever take a class in GRE, these are some of the exercises that we do. And so now I'll show you another illustration, and maybe the kind of illustration that you're more used to, and it's a picture, right? So there's these things called polarizations, and you may or may not have learned this last week, but the gravitational waves will travel in some kind of orientation. Okay, um, in this case, it's as seen as if the gravitational wave is going straight through the screen, and you're on the receiving end of it. So it's like if you're looking down, it looks like a circle. The reason why they use a circle is just because of its geometry. All of those points represent individual masses, and they're not attached to each other. So there is no interaction, or mostly no interaction between any of those particles. So there are these free particles, and they appear to be elongated and stretched in a particular direction. Well, there's also another polarization, and the first one we saw was the plus polarization, and this one's called the cross polarization. You can see it kind of looks like the way that it's being stretched and compressed kind of seems to make this X shape. The thing is, life isn't usually that simple. So one of the most mind-boggling one is, or ideas, is trying to combine both concepts visually. And I think this looks so cool, and I hope you do too. So this is an illustration of what traveling gravitational waves would look like. The rings are shown there as for illustrative purposes, but you have to think of individual masses actually, spread across each of those points. It's like a grid line showing you position. Now imagine if you were trying to use a map that was doing this. Luckily, right, the effects that we feel or that we see are usually not this aggressive in the change in the coordinate systems. So But now it's how do we measure these gravitational waves? And for context, I provide a little bit of history, right? So here we have these things called resonant mass bars, or something that were developed in the 60s by this guy named Weber. So they're called Weber bars, and I believe LIGO has one of these Weber bars outside of their one of their education places, just in memory of that first step. And so the idea is that you have some resonant mass, right? So this may seem familiar, right, if you're studying how to do like Lagrangians and such. So we have an equation of motion for a resonant mar. First term's acceleration, next term's dissipation, and the third term is restoring force. If everything was fine and dandy, then you can say set that equal to zero, and then we're on our way. But in this case, we're adding some external force. And the idea is that we add the external force as caused by gravitational waves. So here we have this two mass model, right? So I have mass one, mass two, and there's some spring that's attaching both of those things, right? We measure this thing for non-free masses we call mechanical strain. And the word strain is what I want to emphasize in this, because this is the measurement that is used for gravitational waves. They talk about things in terms of strain. And in this case here, the actual mechanics behind how the Weber bars were picking up that displacement, right, or that strain, was with piezoelectric crystals. Um, okay, and now we have the interferometer design. This is, again, it was also, the concept was developed back in the earliest work in 1956, right? So around the early 60s. Lasers, right, were fresh, and they made the most complicated way you can make a laser back in the early 60s as well. And the first paper was published in 1962. But here, what we want to measure, the thing to detect is displacement. So how, and notice I removed the spring between the masses. So how do we measure the displacement? Well, we use this thing called an interferometer, and you see here it goes by steps: 1, 2, 3, and 4. 1, the light comes from the laser. 2, it hits the beam splitter, and it reflects off the mirrors that are on the opposite ends of what we call arms. Then the light comes back on number 3 and recombines, and it hits this photo detector. Step 4 shows the effects of gravitational waves, where one, again, keeping in mind, right, the stretching and compressing that happens in particular polarizations, um, you have this effect of the arms changing length. Here is how we measure strain. So we used H to refer to mechanical strain, but here we're talking about this interferometer. So strain is, here we refer to it as the ratio of the change in length versus the length of the arm itself. So, but that's hard to measure. And so instead of measuring the change in length itself, we measure a change in phase. And by doing that, what we have here, right, we see the two arms are equal length. There's no gravitational waves. So the phase is zero. There's no change. But then the gravitational wave affects the mirrors. There is some compression and some elongation that happens on each arm, each one of the arms. And the phase is now some changed phase, right? So now we have some relation between some change of phase and change in length. Um, in the I forgot what they call it, but in the School of Physics, right? The ideal situation in the ideal school where everything works. This is the way that we would be detecting gravitational waves, but it's not. This is actually a simplified version, even, of the way that we measure gravitational waves. And so you can see the path that the light takes is a lot longer than, or a lot more complicated than it seems in the basic Michelson interferometer setup. Okay, so now an example of approximation of strain. So strain is H. Now we have these terms here: gravitational constant, big G. We have the mass of the system. We have distance from us here on Earth, and we have some speed of moving masses. Okay, this is an exercise, and I put there on the bottom right. It was an exercise developed by Michael Richmond, and the approximation was done by Tevye Creighton. Um, two black holes. We'll say, let's say each black hole is 10 solar masses, right? Then we have this thing that we call the Schwarzschild radius, which is given by that term there, the 2gm over c squared. It's about 30,000 meters. That is essentially the edge of what we call the event horizon. Then we have this r, which is the distance from us to wherever this event is happening. In this case, we say it's 340 megaparsecs. Convert that to meters, right? We use SI units in physics. And so it's 10 to the 25 meters. And the velocity, we say, is relativistic, right? It's a quarter the speed of light. When we toss that into the approximation I showed earlier, we get that the strain comes out to be about 2 times 10 to the minus 21. Okay, now we need to think back. Well, do I have anything where I can relate that to? Let's check it out. That's right. It's that ratio, right? That ratio of the change of length versus the length itself. So we know LIGO set up their arms to be 4 kilometers long. Now, what does that mean in terms of the strain? Well, the change in distance, or that displacement that they're measuring, comes out to about 8 times 10 to the minus 18 for two 10 solar mass black holes colliding, or merging, I should say. If we go to Wikipedia, right, because we know they're always right, you'll see that they have this nice scale that talks about orders of magnitude. And I like to do different exercises and see, what numbers I get. And in this case, it says here it's the upper limit for the size of quarks and electrons. Right under that, we see it's the sensitivity of LIGO detectors. So LIGO being the Laser Interferometer Gravitational Wave Observatory, our approximation by orders of magnitude is correct. So we did the right stuff. But wait, let's go back to the first one. Upper limit for the size of quarks and electrons. Yeah, they're measuring such a tiny displacement. Now comes, we're starting to get a little bit closer to what my interest is, which are these things called transient events. So, what are examples of transient events? Go ahead and list them now in the chat. Transient events. I didn't add the word astronomical just because I'm speaking in context here. So, an eclipse would be an example of a transient event. Confidence. um, question mark next to eclipse. A radio burst, an exoplanet transit. So these are examples of transient events. They may be repeating, but or they might not be repeating. Right? It could be some singular event that just happens. Right? It could be chaotic. It could be a black hole collision. Yeah. So yes, but the funny thing is, in the list that I saw on at least on Wikipedia, they don't talk about black hole collisions, because I don't think that most people right now are used to thinking of gravitational wave observatories in the common sense of the way that, or traditional sense that we think of optical or even radio observatories. Um, so yeah, it goes beyond just these events, right? We have supernovae, we have novae, we have gamma ray bursts, we have transits, right? We have eclipses that happen. These are all examples of transient events, and it's something that we can see, right? And it changes in time. Comets, right? Um, okay, we have this concept of transient events. We have this concept of gravitational waves and this measurement of strain. Now we need to combine both concepts of EM and or electromagnetic radiation and gravitational wave radiation. These are two completely separate regimes, like, or not even regimes. They don't exist in the same place. They're completely different things. Um, yeah, they're completely different things. The mechanism behind how we measure each of them is also different. So the question is, which events are detectable by gravitational wave detectors of today? So I had given a talk recently where I discussed uh, what they call 3G, or the third generation gravitational wave detectors. Apparently, we're still in the second generation, though we've done a lot of upgrades from where we first started and from the first gravitational wave detection that happened back in 2015. So the limit is still this: things that are very massive and periodic. That's as best as we got. We can't measure supernovae, though there should be some kind of gravitational wave effect that we would feel. Why? There's a sudden change in mass. There is gravitational wave radiation that's spilled, but there's no model for it. It's an unmodeled process, and that's why I specify this thing about it being periodic. So in 2013, the LIGO Scientific Collaboration and the Virgo collaboration, both collectively called the LVC, the LIGO Virgo collaboration, um, they had a call for action in 2013 for electromagnetic and multi-messenger follow-up. One that usually gets ignored or kind of forgotten are neutrino observatories. Completely different process from EM, where you're trying to find particles, right, or cosmic rays coming from these kinds of events. For example, Ice Cube is one of the projects that's in one of the poles. So yeah, they're also part of this, trying to find gravitational waves through what they can see. So one exciting possibility for us is this neutron star merger. I didn't repeat it accidentally. It's not a typo. Or we're talking about a merger. Usually when we refer to these things, it's like, oh, it's a black hole, or we just say binary black hole. A neutron star merger, or a binary neutron star merger, right? Black hole neutron star, which was one of the most recent, and there was a lot of buzz happening because they said they think it was a black hole and a neutron star that merged, and it fell right in between this gap of mass that they haven't measured or seen anything fall into before, and they don't think it's normal for it to exist. So we have this massive object that they're not sure if it's like a really big neutron star, because there's a limit, right, to how big a neutron star could be before it becomes a black hole, or is it a baby black hole? Actually, there's nothing there's nothing that can tell us, at least yet, beyond the initial measurements that happened. So now we're on this thing. We're on a hunt that for this thing called the kilonova, and the kilonova is like a nova, but it's 1,000 times brighter. That's why they call it kilonova, right? Um, those people that are participating in this, hunt, are people who study as I said earlier, the electromagnetic spectrum, right? So, or people who get signals from space in the electromagnetic regime. Here I have, you may have seen this before. This image is from OpenStax, and it shows what's observable from space, what's observable from Earth, and that beautiful rainbow, the visible light. When we talk about optics, we're talking about things in the visible light range. And so that very narrow band is just one of the many bands that are expected to be emergent of these kilonova events, where we have two neutron stars colliding with each other. The neutron stars are so massive that the particles themselves kind of just form a soup of charged particles. So imagine these two very massive, large. Actually, they're not quite large either. Typical size of a neutron star is about 12 kilometers. And I think it might be something a bit more relatable that for you guys where you live than it is to me, because the example that they always give is Manhattan, right, in New York. They always say that it's about the size of New York City. And but I've never been there, and it's really far, and it's a long drive. I hope someday to make it to actually experience it myself. Um, but that's the size of it. So if you can imagine, it's the of a typical, a city, right? Uh, just charged particles, when those collide, you'd expect some kind of, of you know electromagnetic spark, if you will, right? In this case, we want to see something, and now comes the optical follow-up. The way that it happens is that the gravitational wave detectors, and here I listed some of them. We have two LIGO detectors, one Virgo detector. There's one called Geo 500, which is a German led gravitational wave detector, but the arms are only 500 meters long. Virgo, I believe, is I think it's 2 kilometer long. In the sky, which is supposedly already in operation. And there's one more LIGO, like the site is under construction, and so it's very exciting. So what happens when there's a detection that's made? They send out a notice, and we sit there listening, waiting to get some kind of notice. So this is something that's actually publicly available. You can check out all the alerts that are like coming in hot off the press. Here, there's as we can see, GRB says 20, 10, 14. 20, 10, 20. Okay, so this is something new. You see, it says enhanced Swift XRT position. So you can get notifications, or you can see these events as they're coming in live. And this here is the GCN is a network of scientists that essentially give preliminary data to share. Okay, these aren't they're not official results yet, because they still need to be carefully analyzed. But there's a lot of people that use these or use these notices as a form, or circulars as a form of communicating very quickly their findings. Let me go back to where we're at, and here we go. And so yes, we sit there listening for a new alert, and boom, suddenly we have an alert, 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 alert. When we get an alert, this is something that's also new. LIGO has this thing called Gray State Database that has existed in the past, but now it's public. There was a time that everything was hush hush and we couldn't talk about it. Anyone who was participating in it couldn't share this information. It was privileged information. But now it's publicly available, so you can see some moments after they make the notification on the GCN, you'll see potential things that are triggered. So, for example, here we see this red one that says it's been retracted. It went through some vetting process, and they said, no, it's not good. So what I'm going to do really quick is I'm going to look for B and S, which are the binary neutron stars. Why do I do that? Well, the typical mass for neutron stars is somewhere between 1.5 to maybe about 2.1 solar masses. So the example that I gave was 10 solar masses. It's almost, but not quite, an order of magnitude difference, right, between the 10 and the 2, or 10 and 1. So that means detecting these, you'll see here, there's a lot of terrestrial noise in this one. This one was retracted. This one there's a lot of terrestrial noise. So these are the possibility of it being terrestrial noise, or a terrestrial source, or a binary neutron star. So the percentages are really low. Then we have this thing called the sky map. All right. The sky map in this case is very terrible. They say, where is it? Well, it's kind of everywhere. Localization is one of the things that we, as people who do follow-ups to these gravitational wave events, depend on, because we want to know, where is it in the sky. So this is the entire observable sky from Earth. And they say, well, it could be anywhere from, what you can see above the equator all the way to the South Pole. That's a lot of sky to try to cover. I don't know if I can do that in a single night with my own little observatory. So we got to develop targeting strategies. How can we, like, what do we do? One, do we cover the whole sky but risk getting low angular resolution? So we'll just see the blip but not actually get any measurements from it? Or do we target very specific things so we can try to get measurements off of it? Well, we have limitations with budget and the equipment that we have, and ourselves we can only cover about a quarter square degree of the sky at a time. So this is something you can try at home, right? At sometime at night, if the sky allows for it, go and hold the moon between your pointer and your thumb. And then imagine LIGO says, and I'm not sure in which version if you can see me or not in the in the video feed right now, but LIGO and Virgo might collectively say, well, I think it's in this part of the sky, and probably most likely around this area here. It's kind of large areas of the sky, right? We're talking about in the order of degrees, and we can only cover a quarter degree for per every image. The thing that we're trying to look is also very dim. So we're talking about something that's between 18th and 20th magnitude. So it's very faint. So that means we got to spend a lot of time actually, long exposures to be able to detect the object itself. So we distribute this list of potential targets based on probability maps, and we're constantly changing the way that we decide. Trying to improve on you know picking which is number one. Right? We have some ranking order, and currently, like one of the most or not currently, but one of the earliest iterations of how we were doing it is strictly just based on the probabilities or the probability map that LIGO provides. So we get ready for our observation for the night. Observers will optimize their list of targets. We look at that list, and the best target might not be up during the beginning of our observation, right? So we have to kind of optimize our list a little bit. This is something that we're currently working on as well, optimizing the lists themselves. We'll get prepared with some stock images, right? Because if this is a transient event, some kilonova, some flash in the sky, we'll see something that wasn't there before, right? So we come prepared with some stock image from some old library or catalog, then we can see, hey, we found something, or no, we haven't. And also, very important, grab some food, grab some snacks, grab some coffee. In my case, I like to take yerba mate. This is the people that taught me how to do my observations were from Argentina. This is one of the one of the pastimes and social interactions that we have. And we drive out to the observatory. Luckily, it's not too far, so I don't actually stay at the site. Um, and then hope you're lucky, right? Hope that you find something, and we keep on watching those GCN circulars. Why? Because part of what we do is we immediately after collecting those images, we have to do calibration on all that science data. Like we need to also take calibration frames and those are standard parts of doing observations. To analyze the data, there are some people that use IRAF. If you know IRAF, you might shudder. um, Installation, I think now is probably easier than it was when I first learned IRAF. For some reason, there must have been some funny transition period, and using Fortran compilers. But now it's a lot easier, I think, to install IRAF. But yeah, I think it's getting traded by AstroPy. It's a collection of packages on Python, and it seems to be developing into this new standard. What's really nice about Python is that we're and now the ease of access for people who are just beginning to program is really nice because you're able to develop a pipeline based on the tool sets that AstroPy can provide, and that's essentially what I did for my master's thesis. Then after we do what we call the data reduction, right? After we process these images, now we can compare to the stock images or images across from different nights because we want to see if there's any change in brightness or any new right source that maybe wasn't there before. Um, if we're taking measurements along different nights and we're seeing all the stars and comparing their brightnesses consistently from night to night or from as time is progressing, then all the stars or most stars should hold steady or be variable if they are variable stars. Um, but if there's one star that's dipping in brightness, then we'll notice that, like, hey, I think we might have found something. And the methods that we use is image subtraction, right? Get one image, get the other image, and if the star fields match, then you should get nothing. And if there's a mismatch, then you'll get something, right? And if you get something, and if you're trying to do this with a lot of images, right? Then it's that's when we start using tools such as machine learning to recognize and search for these candidates. Now, we report ourselves to the GCN, so we let everybody know our preliminary findings as soon as possible. That way, we try to establish limits on targets. We look at different, for example, NGC objects, different galaxies or clusters, depending on what we think it is or what strategy we're implementing for that night. And this way, we work together with people around the world to find the source. Because once we find it, then we all look at it because we want to get as much information as possible. So there was one special time, and it's called GW170817. So this is 2017, August 17th. There was an alert. And yeah, from my understanding, you learned about the issues with localization. So the first to detect it, or actually, these are different detection probability areas. So there's Fermi, and then there's Fermi and integral. So this is from the GRB detections, the gamma ray burst detections. You see, there's this really nice overlap in the sky. So this is great for us that are doing, small telescope findings. When you include LIGO and then you include Virgo, then the number of potential targets dramatically decreases from hundreds to just, less than 20 probably. Then here we start zooming in to the one that uh, the one that we saw. So this here is NGC 4993. And this was something that was super exciting for us because we have images of our own. And so I'm going to share those images with you today. So the data that we collected was from T80 South in Chile and Estación Astrofísica de Bosque Alegre. And these are our counterparts in the southern hemisphere. Unfortunately, it was too far south for like I'm going to go back really quick to the sky map, right? Here, we might be able to get just the upper part here, maybe at your latitude where you are, because we're in South Texas, we're a lot closer to the equator. We could see more of the southern objects that you would be able to see because you're just higher in latitude. So our counterparts in Argentina had suboptimal viewing conditions for this. Everyone did. Why? Because it was setting right when the sun was also setting, and it was below 30 degrees in the sky. So these are not what you want to you want to be looking at whenever you're doing astronomy. Usually, you want to be looking above 30 degrees in the sky, and you don't want to be looking close to the sun, right? But we did it, right, in the name of science, and we got this image. So this image here is a false color image from T80 South data that we have. There, that little plus, right, or right in the center of the crosshairs. I'm going to go ahead and get close to that. That is the kilonova event that was detected with the coincident gravitational wave event. So there was a gravitational wave event that was detected, and 2 seconds later, the space telescopes that do the gamma ray detections also detected it. So gravitational waves, electromagnetic spectrum, two separate things measuring the same thing. And then this is what we call multi-messenger astronomy, right? So once those two things happened, and they realized this actually a little bit late because there was an issue, there was a glitch with one of the LIGO detectors, and I heard the story from the guy. He was walking his dog, and they say binary neutron star merger, and this is a guy that reviews the trash. So anything that glitches in LIGO usually gets sent straight to the trash. And he's like, huh. So when he got home, he checked it out and he's like, "Whoa, this is actually a gravitational wave event. Like you can clearly see the chirp signal, which is like it looks like a little in the frequency spectrum. It looks like a curve. Um, it was clearly identifiable, but because of the trash mechanism they had at that time, since there was that glitch right in the middle of the data, they're like, that's trash. Well, guy calls up his. Oh, so that's a good question, and I am not 100% sure why there is the 2 second delay between the gravitational wave event. I'm assuming it's because the light also has to travel through stuff, causing there to be a slight delay compared to the gravitational wave. Um, yeah, so that's what I think. I might be misspeaking here, but this is my understanding of it because they say from this we got that gravitational waves. There's a question: how fast do they travel? We don't know, and the answer we got the answer here. They travel at the speed of light, which is really cool. It just so happens to match up like really nicely. Okay, something that one of our collaborators did that worked with the images, they did something pretty neat. And so here I have this transition image where I superimposed both of them, and where NGC 4993 is, they added a mask and then they subtracted the light. And so now we see the source by itself, and it's clearly identifiable. When you look at library images or stock images, that was not there before. And so definitely we saw the signal. So it was like really exciting times. And myself, I was given a huge opportunity, which is amazing, which is to go to Italy. They were having an astrophysics conference, and I myself wasn't trained or brought up in the typical astrophysics. Training to grow up, right? And by grow up, I mean academically. That's what I say. We grow up learning these things, which I'm referring to. I was working on my bachelor's degree in physics, and I only took maybe one astronomy or like astrophysics class during that time. And as even as a graduate student, the focus I wasn't actually too strong in astrophysics itself. So I did a lot of learning on the fly. Okay. Space and stuff had always interested me, but I did a lot of learning for science on the fly, and it's fun, it's great, and I think it just makes me a better researcher that I'm able to do this kind of thing. And here I am. I'm working on the code that because there's people that were actively working here in the United States and in Argentina on cleaning up the data. And here I'm seeing using a Jupyter Notebook. So I use Python to try to get the same, essentially just verifying that the same magnitude information they had was what I was receiving from the data for that gravitational wave detection. Um, it was so stressful because we were surrounded by people who study who study astronomy, and we couldn't tell them anything because during this time we were still bound by the confidentiality agreements between uh, between or non-disclosure agreements between LIGO and our institution. So we knew, and people were like, I don't know, we've been hearing this buzz about NGC 4993. Someone posted on Twitter, um, and we're like, I don't know. We just say like just keep an eye out. Maybe maybe if something is there, then I'm pretty sure there'll be a big announcement. But we knew, and I had seen the image with my own eyes. Right. And I was like, oh my goodness, this is so exciting. And I can't tell anybody. And here pictured is my advisor, Dr. Mario Diaz, presenting about the Transient Optical Robotic Observatory of the South. Um, Now, how I got here. How I got here. So if you might have heard a little bit that I was born actually here I was born in Brownsville. I grew up in the town next to it. Both my parents are from Mexico, from Veracruz, and this area here is predominantly Hispanic. It's something like 96%, I think, of the population is Hispanic. I grew up in strong Hispanic culture, and one of the things that was that my dad would always tell me is like, you can do whatever you want to do, just make sure you keep at it. And so with that kind of attitude, I'm growing up, I would watch a lot of TV, but it was mostly science things. I enjoyed watching documentaries. I ended up saying, like, very early on, deciding I want to be a scientist for sure. And I noticed that people who had the title physicist or were along the lines of the shows that I like to watch. So I said, I want to do that. I'm going to do that. And found this magazine article that had, they were talking about proving Einstein's theories, and they were talking about merging black holes. And the image credit actually had my local institution, which at the time was UT Brownsville, Texas Southmost College. Um, and I'm like, this is right here. We're doing the awesome stuff right here. Like the stuff I see in the documentaries is happening right here. So this is where I want to go. And I was given an opportunity. I applied for we had an early college high school program here, so I started with the institution when I was 17, and I've been with the institution since. Don't ask me how old I am, but I did crack a joke once saying that if I've been here for 10 years, does that make me tenured? No. Yeah, but but with this, we're a growing institution, we're a small institution, and there's an advantage to that because we get to work directly with people who are, in the top of their field, which is amazing for us. For them, it's great because they essentially have a sandbox to work with to develop whatever program versus, established universities with very well established programs. It's kind of hard to kind of make your carve your way into that once things have already been established for such a long time. And so with that, I was given that opportunity to work closely with people doing these kinds of things. And so then I got my bachelor's in 2012, and then I got my master's in 2019. I am aware that it is a little bit longer than what the traditional student is, but life happens, things happen, and luckily I've been giving several opportunities similar to the time I got to spend a week in Italy, right, through this entire process. Um, so where I'm at now is that, as given in my introduction, right? I'm assistant director for the observatory. This observatory serves as a sandbox or a test bed for the observatory that we're working on in Argentina. Um, that site is supposed to be completely remote, and my goal is to actually make this completely autonomous, right? So the idea would be to develop some observation strategy that we can then feed to a machine that will interrupt whatever queue in the event that the alert happens, right? So they've the tools in Python allow for this pipeline, right, of listening and actively working on. Um, oh no, that's not the Southern Cross in the background. No, but it does kind of look like it. And that's a good observation. We are looking at the southern part of the sky. It just so happens that our sidewalk is pointing north, and so we're looking straight at the observatory is looking straight south. Um, Coincidence? Maybe. I don't know. But it lends itself nicely for that. And there in the back, you see there's these little domes. We call them mini domes. So the main instrument sits inside the big dome. The dome itself doesn't necessarily have to be that large, right? It's not the size for the size telescope that we have. But the reason why it's so large is because it's an educational tool. We have people, come into the observatory, and it's for mostly for outreach purposes as well. So it serves as an education tool for our community as well as our students at our institution. Now, these themselves, I want to see them be used as that primary tool, right? So we have this huge field of view with smaller telescopes, and maybe collectively we'll be able to find transients a lot quicker in this way, and then follow up with the large telescope that we have inside the observatory. But that's not its purpose. Its purpose is as an educational tool for the students who are taking the astronomy labs. So this is actually where I've been spending most of my time most recently. So I actually haven't done an observation in now over just about 1 year now, because I started focusing on completing my thesis for my master's degree, and now I've been working on the formal education side of our observations and changing the curriculum for the astronomy labs that we offer at our institution. So the idea is that we train the students to become or to learn astronomy by doing what astronomers do. Right, so you learn astronomy by doing astronomy. So the way that we laid out all the labs that we're currently working on right now, we have the first for the first semester completely developed, and it's in I guess beta testing now. I went from teaching one semester for teaching one section for one semester to now I'm overseeing a total of nine, and four of those are directly under my instruction. And the idea is then we give them all the tools to take and analyze data by the end of the semester. And they'll be using one of these telescopes. This is an image that I took last week, and I have proof of the time because you can see us here wearing our masks. So these are two other fellow graduate students that are from our group, and they they it's us, the ones that are setting up all the infrastructure and setting up all the telescopes, setting all the data lines, making sure the network is correct. And the idea is that students will then be able to do remote access at some point to do their own observation from home. And that's about it. Thank you. Are there any questions? I see a comment. Really awesome. Oh, thank you.
That's what
We'll
we
cut
need.
that up. Yes, yes.
Great job.
Cool. Thanks.
Let's have some questions. Come on, folks.
Yes.
Um, so we use Maxim DL with our observatory as the
Mhm.
software to do like calibrations and stuff like that. Um, you said you use Python for your
Yes.
stuff. Yeah. Um, how would you say Python is like user wise? Like,
So, user wise, right? Um, for users, point and click, you're right, is usually the easiest thing, and that's what
right.
Maxim DL provides. We ourselves at the observatory use Maxim, but only for essentially for its CCD tools
Okay.
to collect the images. Um, so my recommendation for that is using Anaconda. Anaconda provides this nice, Python installation. You don't have to think really hard to do the install. It's just point and click for installing things, and it gives you this nice jump start into learning Python with using Jupyter. So Jupyter is one of the things, and you see here it's available for Windows, Mac, and Linux. And I think I went to the wrong website. I think it's just anaconda.com. But they uh, they provide Jupyter, and Jupyter Notebook is an interactive like GUI that works inside your browser. So while working inside your browser, you're able to test little snippets of code at a time, and it works really nicely. How it compares in terms of measurements, I haven't actually since we don't use Maxim, I haven't done a comparison head to head to compare with something like, and that's actually something that maybe thanks, that might be a good project for an undergraduate to do. I'll get someone to install IRAF. I'll get someone to work with Python, and the IRAF person will probably hate me. And I'll get another person to maybe use Maxim to see about getting these to compare the different algorithms. Whenever you use something out of a box, you want to make sure that you completely understand what that it's not just a black box to you, right? You want to make sure that you understand what algorithm or what process is being used, because if you blindly accept, whatever whatever output you get from whatever function, then someone might ask you a question, and you'll be, I don't know.
Yeah. All right. Thank you. Yeah.
Cool. Any
And
other questions? Oh yeah, yeah.
well, yeah. I just wanted to ask, do you know what that constellation was in that picture?
No, I'm not sure. I'm not
Okay.
certain. Yeah, somebody said I've shown this picture before, and someone says, "Is that Orion?" And I'm not sure. And it could even be that the brightest object there might not even be a star. It could be a planet. Yeah,
Sure. Yeah.
but yeah, I need to go back to Stellarium, check my my timestamp to see what matches up with that. So I have a statement and a question. Remote access for your students would be amazing, especially given the current situation. The goal of autonomy would be great, but how reliable would an autonomous site be, especially given how there can be mistakes like happened with the trash and LIGO? So user LIGO has a ton of systems. There are so many systems to make sure that LIGO is able just to function correctly. And so they have an operator that is on site to make sure that all the systems are okay. So that's one thing. In terms of the data, though, the data goes through automatic processes that get vetted by humans. So if you see in Grace database, if I click on, for example, one of the retracted ones, you'll see here they have this red text, and it says EM advocate says event is not okay. Even though it's an autonomous process, they still have human vetting that happens. And so that would be one of the things that would have to happen in order for us to be um, operating autonomously. There would need to be somebody who's essentially on call, and the idea would be, well, it's an autonomous, like in autonomous vehicles, they say you should still hold on with both hands, being observant of where you're going, even though is in some kind of I don't want to say like autopilot, but that's like where it's driving itself. That's a good question. How long does the visible afterglow last? So that's not something that I mentioned, right? So for supernovae, these are things that can last on the order of like decades, right? So it's something where you can see there's the peak is what astronomers are usually most going for when there's this peak in brightness and then the dimming. The dimming can extend for a really, really long time, but that peak is maybe on the order of months. For kilonovae, it's on, and this is why we want to make it autonomous. It's on the order of hours to days. So this process is extremely fast and it's also very dim. Um, and and on the order of hours to days. And so we've only seen one. We've only seen one, and that's the other big the other big deal, that we've only seen one, and so there isn't really much to draw from aside from the theoretical models. And the theoretical models say it's from hours to days. Cool. We I think now I didn't share it before, but we do have our paper, right? So oh, actually, maybe I can look for myself. And I have no idea why it's in all caps. Um, I invite you to explore, right, the archive. The archive is a great tool for astronomers. I learned at the conference that I was in Italy. I've heard people talk about the archive before, but everybody there said, "I'm working on doing this publish." this published paper. Check it out on the archive. This is what everybody was saying, and so this is one of those things that you can keep up to date with the freshest, hottest research that there is out there by going to the archive. And here we have our the paper where look, that's me. Where am I? I saw my there I am. This was really cool because this is on the discovery. Like this was our contribution, the companion paper they call it, to the discovery of the optical counterpart to GW 170817. And in here, what I'm doing now is I'm opening it up so you can see what was published, right? And what was published here we have the sky map. The blue dots were potential targets that we had that would match up. Um, then here it highlights the one of the issues of localization, where with only 2 or even 3 detectors, we're not sure on which side of the world it's coming from, right? So it could be coming from in front of us or behind us. Since they're gravitational waves, it goes through Earth the same way. Um, but talk a little bit about the process that we use. And let me see, where are oh, it's not this one. It is not this one. Okay. So, but here we have the light curves, right? So we have light curves for how long they are. But here you see there's a dip from 21 in magnitude, right? So it looks like it probably goes up to close to 20th magnitude. But this dip is in 4, right? Four, 4 units of magnitude in 6 days. So the dimming is really fast, and since it's really faint, it happens really quick. Um, Other than neutron star mergers, what other alerts do you look for to do follow-ups with? So one of the things that and so one of the things that I was interested in doing more recently, but I kind of got booked with with the astronomy labs, was doing follow-ups to GRBs. The GRB satellites are consistently producing data, and if I could also provide some really cool tool that's called PyGCN. PyGCN is a Python listener that was written by Leo Singer for to listen for these things from the GCN itself. So it's in Python, right? So it lends itself nicely to do this, and it listens for all the different kinds of events, including the GRBs. Um, yeah, there's so currently our observatory does follow-ups. Actually, right now has been focused on doing the follow-ups with for the gravitational waves, but the we will also right, because it's not just the neutron star, we're also interested in the neutron star black hole mergers. There is a chance that as the neutron star is getting ripped apart, that there is some kind of optical counterpart to it. There's so many processes that are potential for creating like some kind of electromagnetic coincident event that might be detectable by telescopes, in both cases for neutron star, and neutron star black hole mergers. Black hole is very unlikely. It's very extremely unlikely, though I myself think that it's good practice for our observers to go through the drill even when it's a black hole merger, because who knows, this one might be the one that has some electromagnetic counterpart to it. This might be the thing that lands us on the cover of Nature magazine or something. I don't know.
Well, I think
When you-
this has been really fantastic. Thank you so much. But we're at the conclusion of our time.
okay, sure.
And maybe if you can give us your email, if you'd like, maybe your email in the chat if students want to follow up, we can take care of that, and I'll send you a link to the talk a little bit later today. So thank you so much.
Awesome. Yeah, it was a pleasure doing this. I have a lot of fun talking about these things.
Yeah, it's fantastic.
Cool. Thanks again.
Thank you so much.
Thank you.
Alrighty. Guys, take care.